All right. Okay, flight control. This is where we're going to begin for today. So flight control, there's two types of flight controls we're going to be studying. We're going to be looking at primary flight controls and secondary flight controls. We'll talk about what those definitions are, understand that we have sets of different sections. They both have their different responsibilities. In the primary control system, we're going to look at three. There's an acronym EAR, like your ears, the elevator, ailerons, and rudder. Those consist of our primary flight controls, and those are responsible for movement around the three axes of flight we discussed in the previous lesson. These are definitely required for flight. You can't go without these. If you have one of these systems missing, you can't control the airplane because that's what it's all about, right? Now, if we look at the secondary flight controls, these are to augment flight operation. These are not necessarily for direct operation of the airplane, like an aileron is for turning, or rudder is for yaw, or elevator for pitch. These are stuff like the wing flaps, or these are the devices on the trailing edge. We can have the reverse of that, leading edge devices on the front sides of the wings. Flight spoilers as well, trim systems we talked about earlier on. These are all assisting operation of the airplane. These are secondary flight controls. So yes, they do assist flight, but they are not directly required for operation of the airplane. Any questions on the difference between the primary and secondary flight controls? It's not so critical that you have memorized the term, but it will come up quite a bit with the difference between the two. We'll talk about each control in great detail. So our primary flight controls, when they're designed to have a normal feel to the pilot. The average person can have make the full motion of change in normal flight regime. So they designed the airplane so that the average person couldn't push all the way forward or pull all the way back, then that control surface is improper. So all the surfaces are weighed, designed, and appropriate so that anyone can operate them. Now, when we operate towards the limit of these designs, so really low speed, really high speed, high G loading, then they can start to become more challenging. We'll get to see those in training. But through the majority of our time, the responsiveness to these controls are pretty strong, they're easy to use, and they're pretty user-friendly. All right, as a review, before we jump into it, the three primary flight controls, that's where we're going to start, is the elevator, aileron, and rudder. Okay. Well, I'm going to jump back one slide, see if anyone remembers the next slide. Right about that. Can anybody online or in person tell me what the three axes of flight we rotate around? Go for it.
Longitudinal.
Sure.
Lateral.
Sure.
And
yeah, those are our three axes of flight. And we're going to move around them pretty commonly. Here they are. We named them. There we go. Well, not there, but here. Sorry. Oh, boy, I can't read charts. Here's your vertical axis, and then your longitudinal axis, front to tail, and then your lateral axis from wingtip to wingtip. We move around all these three surfaces, and we'll notice that the primary flight control is attached to one of the movement around these surfaces. So if we move around the lateral axis, that causes us pitch. That's what we call pitch, up and down. We've talked about pitch before in this class, so we've kind of linked it to angle of attack. Don't worry about that. Pitch is different than angle of attack because angle of attack is relative to the wind, right? So pitch is relative to the movement around our wingtip to wingtip lateral axis. Movement around the axis from the front of the airplane to the back of the airplane, which we call our longitudinal axis, called roll. And there's a flight control for that one, aileron. That's what allows us to roll the airplane. Around our vertical axis, we have yaw. Rudder moves around that axis. Quick review of that. Anyone have any questions again on the three axes of flight?
I think the point here would be questions where you can get confused if they're talking about axis rotation versus
the stability along the axis.
Right, yeah.
I wouldn't stress about the stability along the axis too much, as long as you're familiar with what all these axes do.
Okay.
That's the most important part. The most important part is you can tell me, okay, well, if I want to move around my vertical axis, I need to rotate around that axis, which means I need to use that using yaw, which is the flight control rudder. As long as you can come back to them. And remember, our primary flight controls are the surfaces that move us around these three axes. Okay, we're gonna look at each one first. The elevator, this is what is moving around our longitudinal axis. The elevator controls pitch, lateral, this line here. I feel bad for the folks online. You guys can't see where I'm pointing, but you guys can probably make up the difference. Anyway, so the elevator is the piece that's attached to the tail of the airplane. This is what's going to allow for the pitch up and pitch down. Now, physically, how this piece works is using cables, pulleys, cranks, those kind of things. This was actually moving that surface up and down. Now, this picture here shows the elevator on a, looks like a Cessna 172. This is mounted to your tail, so it causes the pitch up and pitch down moments. We'll talk about exactly how these surfaces work in a moment in terms of aerodynamics. Just know that it's attached to the tail, usually through a series of cables in these smaller airplanes. If you move into jets or more expensive airplanes, you might see systems that operate it using hydraulics or electrical systems. But for these airplanes that we're going to be talking about, we're all looking at cables. Pulling back on the control column brings the trailing edge of the elevator up, and pushing down on the control column brings the trailing edge down. That's how that system works. This is how the elevator makes its stuff do what it wants to. Now, as far as aerodynamic forces, you can see, those online can't see, that the trailing edge of the entire horizontal stabilizer in this picture of a 172 moves. That trailing edge moves. Now, the entire horizontal stabilizer moves. We'll talk about that in a minute. But all the air is doing is coming across the top of that airfoil that you see there. And when it moves up or down, I'm going to skip a slide here quickly. When it moves up or down, it's getting a move, it's forcing the air up or forcing the air down. I'll kind of make an example. If the air comes to the top of the wing, it hits the surface and it gets deflected upward. This is the time we're going to go back to Newton's third law. For every action, there's an equal and opposite reaction. And that's what's causing the actual force on the control. So when you move the surface up or down, think about how the air flows in that direction. If the aileron, or in this case, the elevator, if the elevator is pointed down, that air is going to get deflected down. There's going to be a force back upward. That's what's causing this movement in that section. Now, since the center of gravity is forward of the airplane, it causes a nose down force when it goes down, or a nose up force when it goes down from the tail. Or if you had the opposite direction, a nose up force would cause a nose down movement because where the center of gravity is located here. Does that make sense? That's what the elevator is doing. It's all controlled from the cockpit and the control wheel through connections of cable to the tail. Go ahead.
So is that what they consider fly-by-wire?
No, so fly-by-wire would be an electronic setup. So this is set up with a cable from the control surface to the pilot, whereas a fly-by-wire system is I would make an input to a computer that would then send that electrically to a hydraulic system that actually move that control surface. But good question. It's easy to think fly-by-wire, the wire going to the back. Fly-by-wire means like a wire electrically. Okay, so I talked about the difference between a horizontal stabilizer. I said this term horizontal stabilizer and elevator. Anyone have any confusion between those things? We seem to use those terms interchangeably so far. A little hard to understand that. This trailing edge piece, the one that's in gray for those online on the left picture, that is the elevator. The entire piece on the tail is the horizontal stabilizer, because remember, the entire horizontal stabilizer stabilizes the airplane because the center of lift is aft of the center of gravity, further back. And to counteract that lift, there has to be a force in the opposite direction to keep them even. That's what this entire piece here is, either left or right. That's the horizontal stabilizer. The trailing edge piece on the left one is the elevator. That's what actually causes the nose up and nose down pushing forces. However, some airplanes decided that why don't we move the entirety of the horizontal stabilizer as a whole? And some airplanes do that. That's called a stabilator. Two different designs for the same thing. Common, look at this. Your left picture is a horizontal stabilizer. That's what Cessna designs their airplanes with. That's how most common trainers from Cessna are built. The one on the right is a stabilator. This is how Piper built their airplanes. One's not better than the other, just different aerodynamic designs. They both do the same thing, different perspectives. The nice thing about the stabilator is the entire piece can be moved. This has only the trailing edge moving. If you go fly in a Cessna 172 versus a Piper product, you won't notice a difference. You really won't. You might at slow speeds if you pay attention to it, but pretty irrelevant. Just know that there's two different surfaces out there. The stabilator moves the entirety of the horizontal stabilizer, whereas the elevator is the trailing edge of just a horizontal stabilizer.
And 737s have stabilators.
Yeah, most of our larger jets will do this side, the right picture. It's easier to move that control surface as a whole than it is one trailing edge section when it comes to hydraulics. Yeah, I think that'll be good. Questions on that? We kind of touch more of this as we go through the course. Not too much to stress on. Okay. Some airplanes have different designs of where to put the horizontal stabilizer or stabilator, no matter which way you put it. You can get a tail mounted, like a fin like this. At the top, we call that a T-tail. We can get it mounted to a fuselage, or many airplanes have a trillion different designs. There's advantages to each. You'd have to go ask the manufacturers of why they chose that design over others. Just aerodynamic principles of what they wanted from their airplane. Again, as we move things around, have different designs of things, they have different impacts. It's not critical that we as pilots know exactly why at the private pilot level. Just know that different airplanes have different designs for the same thing. Okay, questions on the elevator. I think we should be experts on how the elevator works and how we can control it from the cockpit. And then the two types of it. Those are our critical points there. Any questions? All right. Okay, the ailerons. I would ask what axis it moves us around, but I feel like you guys can probably figure that out. It's in the slide. The longitudinal axis, this is what causes roll. So we know that the horizontal stabilizer is attached to the tail of the airplane. Now, anyone, where are the ailerons attached to? The wings, the trailing edge outboard side of the wing. So the furthest out portion of the wing. Ailerons, much like any of the other control surfaces we're going to talk about today, are controlled through the same thing. Cables, cranks, pulleys, and tubes that run to them. Like you mentioned, airplanes may have fly-by-wire. These may have electronic controls as you get into more fancier airplanes. Now, my budget keeps me on cables, but as you get fancier airplanes, you get higher in tech. But anyway, our airplanes that we're flying for flight training purposes, every one of the ones in the hangar, they're all driven by cable, just like the elevator.
What's a push-pull tube?
Imagine that cable in a tube, basically, and you can have a push-pull rod in there, one rod that moves back and forth. Most airplanes won't have this. Okay, so when you move, this is a picture of a 172 Cessna's airplane flight control system. When you move the control wheel left and right, there's usually an interconnected set of two that are usually connected through something as simple as a bike chain. It's not actually a bike chain, but it's a link that connects the two of them. That's how generally they're connected in the cockpit. When you move, one moves the other. Same with pitch. Anyway, when they move, there's going to be a series of cranks and sprockets and cables that move your left-right input through cables. You can see here they are coming from the control wheel back towards the pilot, up and then out towards the aileron that causes the surface to move. This is what allows the ability for the aileron to move. It's just cables from one spot to the other. Does that make sense? Okay, cool. Okay, ailerons. Questions on the direct connection between the cockpit control wheel and the aileron itself? Cool. The aileron is attached to the trailing edge of the wing. It's an adjustment of angle of attack over that wing to change the lift. So there's one aileron on each wing. What causes the rolling moment is one wing over that portion of the aileron will start producing more lift and the other will produce less lift, causing that roll. That's what this picture is showing. So in this case, the airplane is making a left turn. You can see the lower left aileron is raised on the trailing edge. And that's what the right picture here is showing. See, it has less camber, if you will, and lesser angle. So remember, chord line and camber, those two terms there, camber the bulge and chord line from the trailing edge forward. This is changing our angle of attack over the wing, the portion the aileron sits on. So where the aileron is, it's producing more or less lift. In this case, in a left turn, the lower aileron, the always lower aileron, is producing less lift. And the right wing with the higher angle of attack, the right wing here in this case, that aileron is now going down, producing more lift. That's what these two pictures here are showing. Can you see how the one on the left has a higher angle of attack than the other one? That portion of the wing is producing more lift relative to the other. Now, for entertainment value, I got an aileron here. This is the aileron off a Piper Warrior. We can actually take a look at this. I'll keep it in the room next week, boxes. This is one wing of the Warrior. It looks big here, doesn't it? When we were walking up the airplane, it looks tiny. This is one aileron piece. You look on the back side, you can see all the connection points where you're actually going to get this to work. There's a little pulley here that connects to the cables on the airplane. That's what this little spot here is for. That allows for its movement like this. That's what keeping everything working. If you're in person in the next few classes you want to, in the classroom, I'll have it here. You can actually look inside and see the structure inside. We have a little cutout here if you want to see the inside of it. But this is the actual piece of the aileron that moves up and down. Pretty big. And again, this is off a Piper product, a Piper Warrior.
Did it fail inspection?
No, this one actually has the dent in it that needed to be replaced. A pilot found it. Maintenance went, that's not going to work. Unfortunately, exceeded what the limits Piper is willing to have. So we had to get rid of it. Unfortunately. They're not cheap or anything. At all. Questions on exactly what that aileron is doing there? Cool. There's one major problem with this. With everything, there comes drawbacks. So with lift, more lift we create, more drag we create. Did you guys see the drag equation? Did you notice it was the same as the lift equation, except we looked at a coefficient of drag? It's the same thing. So those things are correlated. As you produce lift, you also produce drag. Now there's different types of drag. We talked about induced and parasite drag, but remember, we're looking at what type of lift here? We're looking at, what type of drag if we're talking about lift, induced or parasite? Induced, because parasite drag is the airplane, the cables, aileron cables. Yeah, those are things. Those are causing drag. The antennas, those things. And that's what's causing parasite drag. Induced drag is our byproduct of lift. So induced drag is directly correlated to lift. So if we're producing more lift, we're producing more drag. So the faster we go, we're actually producing more drag. Different airplanes have different ways of overcoming that. But each you will. Ailerons in particularly, they produce more lift over that portion of the wing, right? So if you look at this 172 here, you can see there's an aileron on this left side. There's a little diagram of lift and drag. Think about this for a second. On the aileron, in this case, anyone want to get a guess whether we're turning left or right? Making
right.
Left turn, right? The right wing is producing more lift. So in that case, the right aileron is down and the left aileron is up, relatively speaking to each other. That aileron that's in the up position is producing slightly less lift over that portion of the wing, which means its drag is relatively smaller than what is on the other wing. So the other wing has a higher lift portion because the chord line, the trailing edge of the wing is falling down. It's got a higher angle of attack, producing more lift, giving you a rolling moment. That byproduct is more drag because the more lift we produce, the more drag we produce as well. If you guys ever, I think I showed you a drag chart, maybe I did or Derek did, that showed you a connection of drag to speed. If we did that, anyone want to give a guess why?
It was like finding your sweet spot.
Exactly.
Between, like,
Yep.
drag.
Anyone want to give a guess why induced drag is directly connected to speed then? Yeah, why is induced drag connected to speed?
Isn't it just the force equals mass times acceleration, and the acceleration of the airplane is increasing the force of the air around it?
Sure, you're right on it. if you dive more, you dive deeper than what I was expecting. Forces, exactly. Lift, which is your force. Lift is the force that causes us to climb, right? But if we noticed in there, what item is the most powerful portion of lift? Velocity. Because did you notice V was squared? Velocity was squared. So the faster you go at a squared rate of it, doubling faster, lift produces. So drag is highly connected to speed. That makes sense? Faster you go, the more induced drag you have. Okay, so we can agree that airplanes with higher lift produce more drag. So the right wing here has a lot of lift, therefore a lot of drag. The left wing is very little lift, very little drag. Now, can you agree with me? One side of the airplane is trying to pull back the other because drag difference is between the two wings, right? That therefore will cause a yawing moment around a vertical axis. Does that make sense? When you turn the airplane, it actually causes a yawing moment, albeit small, but there still is a yawing moment around that vertical axis. Anyone have any questions on that?
But is it the opposite direction?
To the turn?
Yeah.
It's to the outside of turn, so the opposite direction you're going, correct?
Okay.
Yes. One second. Okay, so like you said, we'll talk about this in great detail, but if you make a left turn, that nose of the airplane from the perspective you're looking at, the initial tendency is to go to the right. So when you turn left, that nose will yaw out to the right side of the airplane. And that's all occurring as a result of drag differences as the ailerons move. Is that not impressive? Our primary thought of aileron is to move around roll, but as soon as you do that, you also induce some yaw. Strange how there's some secondary effects. Good.
So would you put in a little bit of left rudder?
You would. We're going to talk a ton about rudder. You might have just hit the key consideration here. Why do you think we have a rudder? You kind of just hit them. You hit a good point. We also talked about turning tendencies too. There's no reason to have a rudder. Okay, I beat this topic to death. Adverse yaw. Are we good talking about it, or you guys want to talk more about adverse yaw? Questions? Does adverse yaw apply to airplanes that have propellers? Yes. Does it have apply to airplanes that don't have propellers? Yeah, it's all aileron related, right? This is a flight control issue. It has nothing to do with anything beyond it. Your airplane has aileron, its lift is changing, drag's changing. So adverse yaw is directly applied to aileron. Every airplane that has an aileron set up like this, which is everyone in the universe that we know of, has an adverse yaw issue from your 737 down to your 170. They all will have that same problem. I got the final link. Give me 1 second. All right, can everyone online hear me?
Yep.
Okay, good. We shouldn't have any more issues now. I see sorted out our problems. Okay. I was going to ask you what the solution to this problem is, but someone has picked up on that solution. If no one online heard it, which you should be able to. Rudder is that solution to the problem. Rudder is what helps us that adverse yaw. Rudder is our fix. Now, as far as aileron go, there's multiple types of ailerons, and I'll leave you guys up to figure out what type of aileron we're looking at here. 4 types of ailerons. Do not get stressed about this. Just know that there's different types of ailerons out there. Knowing exactly which one it is doesn't matter too much. But there's different types. Freeze type aileron, differential. There's a couple of aileron and rudder airplane out there. The Air Coupe wasn't exactly the greatest success in the world. A flaperon, where we have a mix between a flap and an aileron. They all have their own different needs. They're all very effective at what they want to do. Some of them want to reduce adverse yaw, like coupling aileron input to rudder. We later found down the road it wasn't as effective as we planned in different. We tried.
Do you want?
Okay, so a differential aileron. These are ailerons that move more in one direction than the other, meaning up versus down. Most airplanes are doing this as a means to balance the airplanes out, weight out as far as the airplane goes. It's a balancing mean. So it'll go more up in one direction than the other. This also assists in reducing adverse yaw. A lot of airplanes do this very subtly. If you ever, after class, if we can have time to go downstairs, I can show you one aileron, and when you move it up, it moves up about half the distance it moves down. Just aerodynamic design, how you want to move the control. They don't want you over controlling in one direction versus the other. This is the main aileron type we're going to be looking at. A freeze type aileron. This is one where you push and it has hinges that offset its movement towards it. This allows for less drag as it moves. You'll see that we don't have an airplane in a hangar that could make this happen, but you'll see in some of them that if you look at the trailing edge, as this moves like this, the standard aileron, some will actually come down and grab air in the front side of it, called a freeze type aileron that'll grab more air. It improves the efficiency of the aileron, but it does reduce drag nicely. Not all aircraft are designed that way. Different purposes for different designs. I can kind of show you an example of that here. Here we are. Notice how this aileron is grabbing into the wind in the middle picture here. And that's good. It does produce some drag. It does allow for additional efficiency of the wing as air is able to move around that airfoil. Does produce a little bit more lift. So again, don't stress about it. Just know that these are how our ailerons work. They have multiple ways of working in different designs. Now, if you want to couple your aileron and rudder together, the Aircoupe was an airplane that did that. And it wasn't exactly the most successful of design. Comes to find out that if you do, if you do this in normal operations, it works, but between high speed and slow speed flight, it makes a pretty big difference. And they found that it was not as effective as they had originally planned.
So in that one was the coupled, you wouldn't have to touch the rudders, it would just do it for you.
Theoretically speaking. Now, during takeoff and landing, you still would, but you still would. And that was what became the problem, was they found that even the issue was the connection between the aileron and rudder was cable. So it's a fixed amount. So they're saying, well, if you apply this much aileron, you need this much rudder. But the problem is at high speeds, when you apply that much aileron, you have more air flowing over the wing. So you have more density of air. Therefore, you have more lift over that portion of the wing, so it's more effective at higher speeds and slow speeds. So if you move the aileron this much and you had that much rudder input, it would make a big difference whether you're high speed or slow speed. So it's found to be pretty ineffective and didn't work. It was called the Aircoupe. Flaperon, we talked about the flaps a little later in here. It's kind of what I mentioned it. If you had a trailing edge flap to a wing and you wanted it to assist in aileron movement, you could use the connection between a flap and an aileron. We won't see this in these smaller airplanes. You have to move into pricier airplanes outside of our budget to see that kind of stuff. Okay, this is the Aircoupe on the left, this white and blue airplane. This was the airplane that had the interconnected rudder and elevator. On the right, we're seeing an airplane that looks very strange to us. Have a flaperon setup. Notice how there's a large difference between the main body of the wing and the aileron setup. And it's also over the entirety of the wing. It's acting as a flap and an aileron, kind of almost in combination. And it's also got a lot of distance between it and the wing. As a freeze type setup where there's a lot of airflow around it. Improves its efficiency. It's really good at slow speeds. It does produce drag at high speeds. But again, different designs for different airplanes. This airplane is not designed to go fast, is it? This airplane is, they're mainly looking at going slower.
But it's designed to take off in a very short amount of
Correct.
runway.
Right. So all of your short takeoff and landing capability airplanes will have different functions. You can also notice it has a big camber, meaning a big bulge over the top of the wing. The airfoil, that would not do well at high speed. This produces a lot of lift. So as you get faster, you get a ton of drag. You need a lot of power to overcome that drag. So this airplane is really good for slow speed flight. If you go look at a large airplane, you won't see those kind of designs. They're, a fighter jet's gonna have a paper thin wing in comparison to this. Again, so how do we control these surfaces? We kind of talked about it as we went through. Here's a cockpit of a newer Piper Archer setup called a control wheel or yoke. Terms are interchangeable on almost every airplane. Not all airplanes have this setup. We'll talk about it in a second, but most have a control or yoke. They'll set up mainly for flight instruction purposes, so that you can have one person flying the airplane. And if the event someone else needs to fly it, they can. Unlike a driver or a car where you're doing, I don't know, I couldn't teach someone to drive a car. In like a school environment where people you don't know who they are and you don't have an ability to interact, at least in an airplane, I can still fly the airplane through my seat, but whatever. Anyway, again, how are these things connected to this control wheel? Cables. As you move them, there's a ton of cables. If you're ever at a hangar and you have the ability to go see these cables, go take a look at them if the airplane's pulled apart. We can actually take a gander at them and kind of understand them a little bit better. But that's just a generally good rule. If you ever have a maintenance shop and you go up to the mechanic, hey, you don't mind if I come take a look at the airplane? They're usually pretty nice about it. Not all airplanes have the same setup. Some have a stick in the center, like this Cub here, or a single control column setup like this Bonanza on the right. Every airplane's different. You might see side sticks off the side of the airplane. I don't have one in here. Darn. That's what a Cirrus would have. So different designs do the same thing. All of these control surfaces work the exact same, just different pilot control. Whether you have a side stick, a control wheel, or a center stick, the airplane is controlled the same. You move the stick left, the left aileron goes.
Wait, say it again?
If I turn left, which aileron is going to go up? The left one's going to go up, right? Once you get in flight training, there's an easy way to remember this. If you imagine grabbing, if you're in the cockpit, grab the control wheel in front of you, put your thumb up on either side. If you move your thumbs, it points to one side. That's the side of your aileron going up. The other side goes down. That makes sense? When you go into flight training, we'll take a look at it when we do a pre-flight check to verify they're connected properly.
Does the side stick still use cables or is that
Correct.
hydraulic?
Yep, there's still cables. Yep, still cable setup. Instead of it connecting to a pulley from the end of the shaft of the control wheel, it's connected to a pulley at the end of the shaft on this little side piece. Same setup, just different control pieces that you're using. Any questions on that? Any questions on our first two, ailerons or elevator? Cool. Okay, the next one, we talked about it in good detail in the last few classes. We just kind of gave an introduction to it. A rudder, this is our ability to move around the vertical axis. This motion we call it yaw. Like the other surfaces, this is also a movable surface. It's attached to a fixed surface, the vertical stabilizer, or we generally refer to the whole piece in the back as a rudder. Like we kind of refer to the whole tail as an elevator. Remember, on some airplanes, you have a stabilizer. Some you have a horizontal stabilizer elevator combo. The entire piece is called a horizontal stabilizer. The entire vertical piece is called the vertical stabilizer. The trailing edge piece is called the rudder, just as far as we get terminology out correctly. The rudder is controlled with the rudder pedals in the cockpit. These are two pedals on the floor. And again, surprise, surprise, they're attached via cables. I know that might become surprising. Again, other airplanes may have different setups, but our smaller airplanes are going to be cables, and they're attached to the rudder pedals on the floor. This is a really high-end diagram from the mid-70s that Cessna decided to put together. Yes, the screen is split online. That did swap. I do apologize about that, but you should still be able to see it. Sorry. So you move those pedals on the floor in the back, and it just runs a cable all the way back and adjusts the rudder. It pulls on one side versus the other. What's the next one? I have a rudder here. This rudder reached its lifetime. Reached an expansion, had a crack in it. As with everything in metal, goes around at the end of time. This is the rudder to another Piper Warrior, happened to be the exact same one. This is the tail mounting point. These two pieces here is where those cables from the cockpit floor are actually attached. So when you move them, that causes this rudder piece to move like this on the tail. Not as big as you might think in comparison to the aileron, but this is a rudder. Cool to have, we'll show and tell
Just
sometimes.
keep bringing out these different parts.
Yeah, I will run out. Eventually we'll have to get an actual airplane. I would have brought the propeller over on the last lesson, but that's way too heavy. I don't know how much it is, but too much. Too much is the correct
How
answer.
often do those cables need to be changed? Or they are,
There are time limits on them. I couldn't tell you what the time limits are, but they are inspected at every annual inspection. And if you operate aircraft for hire, every 100-hour inspection. There's inspection holes all across the airplane that are removed during it, and they look at the cables to ensure they're not fraying or damaged. We have had ones that frayed over time just due to age. They've been around for a while. And replacing them does take a while. It's a pain to route the cable through everything. They're also under tension and have the right weight on them, and they're balanced. So they're a lot of work to get in and out. But again, if they don't work right, they got to be replaced. So here's those two rudder pedals. This is out of a Cessna 172. You got a left and a right pedal. Again, dual pedal setups. I have two. You have two. Both pilots have at least two. One left, one right. As you push the bottom sides of the pedal, indulge me for a moment. As you push the bottom sides of the pedal, that causes the rudder to move left or right. Let's talk about some kind of like the ailerons, walk through it. If I push the left rudder from our cockpit perspective, where will the airplane yaw to, left or right? Left. The nose goes left, but the tail comes right, right? Because as I push left, the rudder on the tail deflects towards that side of the airplane, which causes air to deflect that direction. Newton's third law of reaction off direction, that pushes the tail in the other direction. So when I press left rudder, it's moving the aileron, the rudder to the left, which causes the tail to go right, which gives me the left movement in the cockpit. So it makes sense to us. When I push the left pedal, we go left. When I push the right pedal, we go right. Does that make sense? It's a little bit of a mind connection to make a second. The reason I said the bottoms of these pedals is because the tops of the pedals are connected to brakes. We'll talk about that during hydraulics at the end of this lesson. We talked about this. I don't think you guys have much question on exactly how the airflow works here. You think we covered that one? Can we agree? Questions? Cool. Again, this is what is gonna fix our adverse yaw. So when we turn the airplane, you need a little bit of rudder. You'll learn this pretty on in your flight training, how much rudder to add, or if you're adding too much rudder. Also, beyond the adverse yaw during turning, the rudder also counteracts all those left turning tendencies, the torque, the gyroscopic precession, the P factor and spiral and slipstream we talked about on Tuesday. The rudder will be that effective too. Any questions with that? Okay, I'm going to do my best to play this video. This is from a great flight instructor, Rodney Shadow. He talked about the flight training application of adverse yaw on the rudder. See what I can do here. If I have the video in the slide, which it does not appear, I have the actual video in the slide. Isn't that nice? I can cover the solution to that topic. What he goes on to say is this. It's a shame, he's a great flight instructor. What he goes on to say is, as you're flying along in cruise flight and you add left rudder, you'll notice the airplane's nose yaws to the outside of the turn, or to the right. The opposite direction of the turn is where the nose's initial tendency is. That's all because of aileron. And all you need to do is, when you turn left, add a little bit of left rudder in that direction. Has anyone actually flown an airplane and seen this in application? Can you guys share your experiences on it? Anyone want to go first?
Makes it a lot easier to make the left-hand or right-hand turn when you use the rudder.
Yeah, it does,
Make a
doesn't it?
turn, but you give a little bit of rudder in either direction, and that plane just, it wants to turn by itself.
Right, right. Have you noticed maybe a difference at high speed versus slow speeds?
Probably high speeds, you're gonna get a little reaction to it.
Yeah.
Because of the velocity.
Yeah. Would you consciously notice that when you're at a slower speed, you'll need more rudder input to have the same aileron input?
Probably.
Yeah, and I only bring that up because as we get slower, there's less air flowing over the rudder, so there's less air being deflected, therefore less force.
Even in the direction of
Yeah,
you're doing your circles.
yeah,
And there's a north wind,
sure,
so it's gonna change from the north side than it is to the south side because
sure,
of the wind.
sure. So what we want to consider is that as we turn the airplane, we need coordinated rudder input in the direction of the turn. Too much rudder and we overcompensate this, as what you were talking about between slipping and skidding, or too little rudder, depending on which one you're looking at. Got that? Make sense? Cool. All right, we're going to jump out of primary flight controls. Questions on primary flight controls that you're just dying to ask? Okay. Secondary flight controls. Unlike primary, secondary flight controls aren't the most necessary things when it comes to flying the airplane. They're nice to have things. We certainly will not fly an airplane without them usually, but the airplane will not come out of the sky without them. They don't move us around our primary axes of flight. These are things like wing flaps. Unfortunately, I was going to grab a wing flap, but we didn't have any in the maintenance office right now. Don't. Leading edge devices. Very few airplanes we fly have leading edge devices around here. Spoilers. There's actually an airplane hangar with spoilers attached to it, but I can't bring the whole airplane up here. And trim systems, we'll talk about trim pieces. At the end of the class, and when you guys who are online are gonna come next week, come take a look at an aircraft in the hangar. And you'll be able to see what that looks like, by looking at an airplane down the hangar. These relieve control pressure inputs and improve the flying characteristics of the airplane. For example, flaps get us to land slower speeds, leading edge devices do the same thing, spoilers slow us down, and trim systems allow us to reduce control pressure inputs when flying.
Which plane has the spoilers out there?
There is, I believe, a Lancer.
Okay.
I believe it's its name over here. I believe that's what it is, a Lancer. Much faster airplane than what we're normally used to. Okay, we're gonna start talking about flaps. This is our biggest secondary flight control. It does lead to a lot of confusion on exactly how it works. It's pretty simple. We call them in most places, when you leave the small general aviation world, high lift devices. If you go read any of the FAA's documentation, or you get curious and go read an accident investigation, they're going to say the aircraft was equipped with different high lift devices. Flaps is a high lift device. Trailing edge of the wing is where we include these flaps. If you could probably assume high lift device means it produces a lot of lift. Now, I'm not going to get into the aerodynamics immediately too much. I'm going to wait 3/4 of a second, but I'll at least give you guys a moment to think about this. When the trailing edge of the wing falls, where an aileron is coming down, it's starting to have a higher angle of attack and produce more lift. That's what the flaps are going to do over another portion of the wing. So flaps' primary purpose is us ability to get in and out of airports, shorter runways, have steeper approaches, and fly at slower speeds. They produce more lift and more drag. In terms of different designs, we have plain, split, slotted, and Fowler. We'll talk about each individually. I think we got these kind of things. It does have a chord line change as you move that trailing edge of the flaps down. When we talk about boundary layer separation control, does anyone kind of have an idea of what boundary layer is? We talked about it in lesson 1, I think. Airflow separation. Yeah, so as we slow down the trailing edge of the wing, that airflow becomes turbulent and no longer attached to the wing. One way to keep it attached to the wing is allow the air to have more of an even path as it comes about the bottom of the wing to follow. You notice the flaps follow that natural airflow to allow it connected for a longer time, which gives us the ability to fly at slower speeds. Some flaps increase the wing area. Anyone want to have an idea of what that has an effect on lift?
Bigger surface area.
Exactly. If you go back to the lift equation, we had S sub A surface area. I believe I had it as the variable in there. More wing you have, the more lift you have. Some flaps increase wing area. You ever notice on an airliner how the wing seems to grow backwards and down? It's producing more lift and allowing more lifting surface. We'll talk about one of the Cessna 172 has an airplane with flaps that actually increase wing area where Piper products don't. Not critical, you know that, just cool fun fact. Okay, we're gonna talk about each of them. Plain flaps. This is where we take the trailing edge of the wing and just drop it down straight from there. Nothing fancy about this. It gets the job done. It does exactly what we're looking for. Not a common design. This produces a lot more drag than the other versions. This air hits here and goes straight down. There's no relief of that airflow on the front side of that airfoil. It's, there's no way for that air to go around. It's got to get forced down, which does produce lift. That's great and all. But it also produces a lot of drag. So it's not the most efficient design, but we do see it out there. Stepping up a little bit, we can go a little further down the road and get into split flaps. We won't see this one much. We really don't see many aircraft with this design. This is where if we were to add a secondary piece to the wing on the bottom side, and we call it split, because it splits the difference between the wing and the control surface for the flaps. These produce a lot of drag as well, and they cause a lot of turbulent airflow down here, kind of like the plane flap, a little bit worse based on its location, because this airflow wants to continue like this, where this airflow doesn't. So there's a lot of turbulent air back here behind it. Just by design, it wasn't the best design in the world, but one way of doing it. But what are you gonna do? Everyone has different designs for things. Slotted flaps. This is one of our most common popular flaps you're gonna see out there. These are gonna be the same, very similar to a plane flap, except air can flow above it. That allows for more airflow over that airfoil and more lift, which also does produce more drag. Because that airfoil is gonna produce lift perpendicular to its cord line, which means you get more lift off, but you're also producing slightly more drag from it. These are more efficient than our plane design because the plane does not allow any air movement over it. Very inefficient aerodynamically. Whereas this one does allow it. This again just takes the trailing edge of the wing and drops it down. There's no added wing area from these. This is your common design you'll see on most Piper products. After class or on the next one, you can ask your instructor. I'll go down there, I'll show you guys what the Piper flap does. You can see it drops exactly as this picture does. Questions?
On that plane flap you had on there?
Sure.
If you had your flaps down and you're going into a turn, what would that do to your air? Because if that air is just not going down, it's going around that flap as well.
It does, but most of this air will get trapped on the bottom and get deflected down like this. There is going to be a little bit moving around the edge, but not a significant amount, just as much as any other flap. Most of the issue here is that this air gets here, gets stuck here, has nowhere to go, so it's forced down. That causes the drag portion of it. Not that it's not necessarily going over the sides. Even in a turn, it still has the same force. Did that answer that?
Yep.
Okay, Fowler type flap. This is what you're going to see on larger airplanes and our Cessna 172. Major difference is a Fowler type flap, again, has airflow over the top, so we know that one. But its difference is that it actually increases wing surface area. So it's a type of flap that slides backward on a track and expands the size of the wing. These are great because it produces a lot more lift. This is most aerodynamically friendly. We'll see this in the Cessna 172. Now, I didn't mention it so far, but most flaps are controlled either mechanically, electrically, or hydraulically. Like a Piper product or most Piper aircraft you'll fly, they will be controlled with this little piece here. That will be usually mechanical. You move a handle in the cockpit and it just mechanically moves a couple of cables and linkages, and that's what causes it to move. A lot of Fowler type flaps that extend outward onto a track, they can be mechanical, there's no doubt. But most of our training aircraft, when I'm referring to Cessna 172, operate this through an electric motor. So they're electrically driven out and back. So if you have an electrical failure, you can't use it, your flaps don't work. Whereas in a Piper product, you can still use it. Nothing bad or good, just different design. You can still land the airplane without flaps, you have a higher approach speed. If you take a combination of these two, I can't tell you exactly what airplane we're looking at here, but any airliner, name the one, we'll have a flap set up like this. Notice there's different sections of flaps, and they have little seals and gaps between some of them. This is a difference between this is added combo, slot and Fowler put together, a slotted Fowler flap. This is what's going to be your best design for your heaviest high-speed airplanes. The heavier you get, those wing designs that an airliner would fly on, they're really not designed for slow speed flight. That's not their design. Like we said, like a Piper Cub who's got a wing with a big camber over the top, that produces a lot of drag. Airliners are designed to produce a lot of lift at high speeds to move fast. Those wings aren't designed at slow speeds. There's a bit of a trade-off you have to have. So to fly at slow speeds, these are the guys that have a ton of flaps. So airliners will see a lot of flaps. Our airplanes are designed for slow speeds, so flaps are the most important thing in the world, but we'll use them all the time. You'll get to see its impact quite a bit. Any questions on that? Cool. We talked about this. Here's your 172 flap handle or lever, if you will. You can move that up and down to select settings, all electrically driven. This handle here called Johnson bars, or old classic term. You press the button at the top of it to press that and pull it out. This is what's moving the trailing edge flaps. Now the right side, we have your typical airliner setup. It's just like you're selecting, just a handle. Really nothing too fancy, but they removed the cool portion of it as you get into fancier. So this is electrical. This is mechanical, and this is hydraulic. But it's still an electric just different ways of doing it.
So when you get, so I can see 10 degrees, 20 degrees, what is full, 30 or more than?
Depending on the manufacturer, usually 30, 35, maybe 40 degrees. Most 172s at 30, 35 range. Older models give you the 40-degree flaps. They found that it produced so much drag that pilots who attempted to go around at that flap setting usually lost control of the airplane due to how much drag they caused. So Cessna said, we're just going to limit it at 30 degrees. So there's very few airplanes flying around with 40-degree flaps available still, but they're out there. There's guys who want them. So you modify your airplane, you certainly do it. But usually about 30-degree angle. Okay, leading edge devices. We're not going to spend a ton of time on this. These usually don't apply to us and won't come up in any of the knowledge tests or any other sources. Your examiner will not ask you about these, but no, they exist. Leading edge devices do the same kind of thing. There's a couple different types here. You can pretty much have like a leading edge flat in any sort of setup. These do the same thing that a trailing edge flat over the leading edge side, usually larger airplanes. The purpose of these is usually to delay stall by allowing airflow to flow smoother over the wing, and that allows us to fly at higher angles of attack before we stall. It delays the critical angle of attack from stalling. I don't think I have a slide on it here. I do. Let's look at this picture. The main core idea of this is this wing flies on air flowing over it. So we want the maximum amount of air flowing over our wing as possible. You'll see the term energy adder device if you go look in the physics world. That is what we're meaning is we're adding energy, which is going to be airflow, more lift. So if you can add more air into this wing here, it gives it more air to work with and more lift to produce. That's all this is doing. This is directing more air further after the leading edge. It's hitting the leading edge, bring it out, allowing more air to come up over it. This allows us to fly at higher angles of attack that would not reach the critical angle of attack earlier. It delays your stalling speed essentially. Now, if you fly large airliners, that's mainly so that the airplane can fly steeper approaches and fly at slower speeds because again, this wing is not designed for that. If you jump into short takeoff and landing, leading edge slots or cuffs like this do the same thing. They add energy, they allow for a delay of the critical angle of attack. This allows us to land at shorter takeoff lanes. We're producing more lift and we can land in shorter distances and have steeper approaches. That's what the leading edge device does. Don't stress about it. None of you will be asked about it from pretty much here on when it comes into the private pilot world. I don't really care about this. We won't stress about leading edge devices too much. I said it was delaying the critical angle of attack, that position. Here's an example of that. So this blue line here is a plain clean airfoil, no flaps. We can see that as we increase our coefficient of lift, eventually we reach a maximum. That's our critical angle of attack and it begins to go down. If we add that same airfoil with slats, but not flaps, we can see we can delay it a little bit further. And then if we add slats and flaps, we can delay it even further. It just allows the airplane to fly slower than we would otherwise. Questions? I feel restricted standing up in this one corner. I need to like walk more. Okay. Spoilers. These got one big purpose. These are high drag devices. So we've been talking about how to produce as much lift as we can by minimizing, while minimizing as much drag as we can and dealing with its effects. Now, these are times we want to produce a lot of drag. Think about a glider here. These gliders, if they get faster, they can't really control their speed and descend at the same time because if they go downhill, they accelerate, just like everything else in this universe. So they need some way to slow down. So these will do that. Airliners will use these flight spoilers to slow the airplane down on landing and in descent. The whole purpose of spoilers is to spoil lift, which causes that drag. It reduces its smooth airflow over the wing. Think about the air smoothing flowing smoothly over this wing. That fence generally stops that. Also think of it as a force that's going to direct airflow up, which causes a downward force. You can see that right here. All that turbulent air behind it certainly causes a lot of drag. So these are in use to slow the airplane down or reduce landing roll, either depending on what your design is. You won't see this until you're flying an airplane that has some speed. That Lance Air out there in the hangar can go pretty fast. I want to say, I'm not entirely familiar, a little over 200 knots. Don't take my word for it, but something faster than what we're normally used to. If you're in a descent on that airplane, again, that wing's designed to fly faster than a 172. If you want to slow down, as you slow, that wing doesn't produce as much drag, so you need to find drag somewhere else. The spoiler is the way to go. Next control surface, we're going to talk about trim. So we talked about flaps and leading edge devices. Those allow us to fly the airplane in different conditions, steeper approaches, delay or critical angle of attack and fly at slower speeds. They have great functions. But when I'm flying around, anyone actually flown an airplane and talk about trim? You guys actually, who wants to talk about it? Someone? Go for it. You seem like you want to. Go for it.
Yeah, it's really just like a make your life easier type thing. Adjusting the controls that would need to be held otherwise, so that you don't have to keep adjusting the inputs, just straight on a flight or in any other constant.
Right.
Constant movement.
Right, like if you're in cruise flight, as we level off in cruise flight and we begin to accelerate from climbing speed, the airplane is going to accelerate, which means it's producing more lift because it's increased velocity. So as we accelerate, you actually have to push the control forward. And eventually, as the airplane stabilizes, you're holding all this forward input. Well, you can actually remove that input by trimming the surface. This is going to minimize our workload. Most airplanes only have an elevator trim that we'll have in our world. That adjusts their pitch. And it slowly moves the elevator piece in the tail. Larger airplanes, you'll see rudder or aileron or roll trim, depending on what your airplane is. There's a couple different ways of doing these. We have trim tabs that are either movable or not movable, so they're called fixed trim tabs. We may have balance tabs that balance the airplane out. That's their only purpose. And some anti-servo tabs. Just different ways of doing this for different purposes. We'll talk about each of these in turn. So a general trim tab, see this entire horizontal stabilizer piece here. You can see this little cutout. Again, after class or next class, you guys can ask some, you're not here. We can go move that trim tab. Think of this. You know the horizontal stabilizer, that elevator on the piece flies the whole horizontal stabilizer as it moves up and down the flex air. That little piece on the back does the exact same thing, but to the elevator itself. So it's like another elevator on it that allows for small input that makes that change for you. So when you move the trim tab, it's permanently flying that elevator into position for you. It's reducing the control input you have to hold. That's what that little piece on the tail is. This trim tab that we're talking about is a movable one that we can adjust from the cockpit. Right here in the cockpit of the 172, there's an adjustable wheel that you can make that change with. As you move that trim piece nose down, it'll adjust this trim here to allow the surface to give you a nose down force. As you trim the other direction, give you a nose up force. Now, exactly how they all move is going to take a little bit of more mental thinking here, but I'll give you a moment. Here's a nose down trim. See how the trailing edge moves? This is way over exaggerated to what's actually moving. It only moves like this much. It's not really much, but makes a big difference. This picture here is what's showing you that slight movement on the trailing edge. Does that make sense?
So the trim is on the elevator itself.
Yes, the trim tab is physically on the elevator of this particular design, which you'll see in most.
It's like trimming on a boat.
Yeah. Yeah.
And the boat will stay like this until you trim it out and you're forcing the nose down.
Right. Nothing too groundbreaking here. And the reverse direction nose up, it does that. It's all working on deflecting those forces, adjusting the angle of attack over that piece of elevator and causing the lift change. Make sense? Does that click? Does that make sense? Cool. Okay, this is a good video where you can see that trim tab operation as you move it. The pilot is not moving the elevator here for reference. We're just moving the trim tab. Air is flowing over that entire stabilizer. As you move this, it forces the rest of the elevator to move, just aerodynamic forces as you push it. This is a good video, all things considered.
So you'd see the action on the control stick where you're.
Yep, you could feel the change in the force of the input as you move the trim
It
wheel.
moves out. It's just.
Yeah.
Yeah.
We'll say in flight training like 1,000 times, but you really never want to be flying the airplane out of trim. Meaning if you're pushing the airplane down, you're having a lot of force, you should probably give it a little nose down force. It reduces your input, keeps your workload down.
The problem people run into is with autopilot
Uh-huh.
and getting into nasty weather and
Sure.
the autopilot's trimming it
Sure.
and then it shuts off.
Yeah, there's a lot of autopilot issues. We talked about that in one of these lessons. I think it's the end of the flight control section, very briefly. But we're not always the only one as a pilot making an input in the elevator. It can also be an autopilot trimmed input. Most autopilots have a little servo, a little motor that moves that can adjust the trim for you. Some do, some don't. You will. Not the most critical thing. Whether you move it or a little electrical motor that's connected to the autopilot move it, it's still moving. Still doing the same aerodynamic purpose. Another one is a balance tab. I don't have an example of a balance tab. You usually find them on ailerons. But I know we have airplanes in the hangar with them. Essentially what you get is, sorry, I'm not on camera here for a second. The trailing edge of the aileron will have a little piece of metal that will hold out in the backside. So it'll just sit here permanently. That is a balance tab. That adds additional aerodynamic force to that aileron or that surface that allows the surface to balance out. It's been placed there by a manufacturer, maintenance verifies it. It's been placed there to balance the entire control surface out. Now, if the surface is out of balance, maintenance can add weights on the inside of the aileron or rudder or elevator, whatever piece you're looking at, that allow it to balance out. But some airplanes have permanently established balance tabs in place.
What do the weights do? Is it drop it down? Just
Yeah, balance the aileron out a little bit.
Okay.
They can also adjust the physical aileron's neutral position while sitting neutral as well. We'll adjust those things on the ground. And there's when the maintenance manual, when they have it has a set angle they should all be sitting at, and they'll put a little angle measure on them into its time. Balance tab does the same thing. Difference is we can't adjust a balance tab that's permanently not there. Kind of like this. Here's a fixed trim tab. This is what we'll see on a rudder. So on a 172, you'll see this little extra piece here that's extending off the rudder of the airplane. That's purpose is to mainly, in this airplane, counterbalance the turning tendencies of the propeller by design. I got to fly maybe 2.5 years ago on a special permit to fly an airplane. We had an issue where pilots were saying, yeah, I never need right rudder. I feel like I need left rudder all the time, and I should need right. Something seems off. Turns out this adjustable trim tab was out of balance. So maintenance put it back. I went to fluid, it's totally fine. But believe it or not, this tiny little piece, it's only like this big, makes that big of a difference aerodynamically. You can actually change the entirety of the rudder and put it in the airplane. They don't want it neutral input because then you have strange rudder inputs the majority of the flight. They want just input during high power settings. Reason being is they essentially want a cruise flight, very little input necessary. Otherwise, you'd be holding your foot in the entirety of the cruise flight to balance itself. It's designed for comfort. Like I said at the beginning, normal feel for most people.
So in that picture, it looks like there's only one trim tab, which is on the right side.
Yes.
Okay.
It's they only put one on here. One is effective enough to flying both. More parts, more weight, more things to fail, more money. They want the airplane as cheap as you can to sell it for. I mean, these things come out of the factory 172 today for I want to say 700,000. I mean, they're not cheap. $500,000 for one of these brand new to fly around at 115 miles an hour and bring 4 people on 180 horsepower. Anyway, yeah. One is sufficient on the rudder as well as there. Questions on this one? This one we shouldn't touch. Some of them actually have a sticker that says don't touch. These are permanently bent in that position per a standard in the maintenance manual. An anti-servo tab. This one's a little more complex to understand. You know how I said that there was different types of elevators out there? I said there was a horizontal stabilizer. There was a straight horizontal stabilizer combined with a trailing edge elevator versus the entire piece that moves. I call that a stabilator. These are where you'll see those anti-servo trim tabs on stabilators. These pieces move in coordination with the entirety of the horizontal stabilizer or stabilator. As I move the surface up, the trim tab comes up. As I move the surface down, the trim tab goes down. Now, when you move the wheel in the cockpit, it does physically move that piece and it limits the range it moves in. Different design. Piper is the one who selected this one in their design. Nothing wrong or right with it. It does the same thing, except it moves in coordination with the entire surface. Only reason they did this is since the entire stabilator is moving at once, they needed to move it in coordination with its angle of attack change as a whole. So this moves in coordination with this. It does the same structure though, same piece. This entire section is the trim tab. We'll call that an anti-servo trim tab. There's a servo that runs it, that's why. Questions? Again, this is another one to look at in a hanger, so it's good to look at. As far as moving trim tabs, we can move them manually, but some come with electric trim. So instead of having to move this handle, this wheel usually all the time, some of them come offset with electric ability to spin that handle, called an electric trim. And here's what like a typical airliner would have, it's a button. We have the same thing, it's off of Bonanza. You can move it in the cockpit. Any issues you guys think might come with this? Loss of power, sure that could do it. Most of those would usually have some form of a backup to it, right?
Easy to bump.
Easy to bump, yeah. We would think they're easy to bump. I mean, they are easy to move. But if you go after this, I'll show you guys. So you go down to 172. There's this switch is split as there are two switches, a left half and a right half. You have to move both of them to actually get the trim to actuate, and it does require a good bit of force to move. So it's not like a light pressure input will do that. And you got to move both. You can't move one at a time. That would tell the system nothing. You need to move both. It's all safety input. Major issue. These are little switches. If dust or dirt gets on the inside of them, the electrical contacts touch and they run. So if you're in flight and the trim contact gets connected and it starts running the trim, the airplane's nose will aggressively go up or go down. It's called a trim runaway. Pretty bad for airplanes because you pretty much lose the ability, like you'll be flying along cruise flight, the nose will start going up, you push forward and it keeps going up because that trim piece is still running it up just due to a contact issue here.
Having stop.
Pull a breaker, disconnect the system, whatever that specific airplane setup is, depends on how that airplane runs its trim setup. I mean, they're all going to be some form of electrical setup, so usually it's an electrical system. It also could be a trim system circuit breaker or a button in the cockpit you can press to disconnect them. Sometimes they're not always pilot inputs. If you move into the larger airplanes with these things, you'll look at augmented inputs with trim from a computer to assist the pilot flying the airplane to keep feel. If everyone remembers the Boeing issues with the 737, their MCAS system, that was an automated trim setup that ran pretty much a trim wheel for you and did these inputs. Unfortunately, their inputs were not calculated properly and had some issues, but they would accidentally run away and run to the full limit, losing control of the airplane momentarily. It was all a stall protection thing. Pretty much they said, hey, if you got an angle of attack pretty high, because the airplane monitored angle of attack, it says, hey, if you have an angle of attack, we'll say if the critical was 17, they're saying, like, if you get an angle of attack of about 13, you need to push the nose down. And they said, oh, you know what would be really smart? We won't let the pilots do it. If they push the nose up too much, we'll just automatically trim the nose back down and cause the airplane to go back level.
Because the motors are forced too far forward
Yes.
and they're worried on takeoff that they would stall it.
Yeah, maybe one of those times. It's a ton of different times where that system would kick off. But yeah, it comes with risk. That's what I'm trying to get at here. It comes with risk. So keep your airplane well maintained. An autopilot is something that will keep the airplane doing everything we want. It's not, you don't need it. Flying these small airplanes, you'll find you can fly for 2-3 hours and it's not a big deal. Now, if you're flying 3, 4, 5, 6 hours a day, every day of the week, say you're traveling or working for something or traveling for business, yeah, it's gonna be tasking. Or you're flying in instrument conditions where you can't see outside, it's definitely a lot more tasking. So an autopilot comes in handy. It's a good workload reducer, not a requirement. All these autopilots work on is they manage the flight controls through mechanical servos. Everyone familiar with a servo is when I say that term? Anyone not familiar? Okay, so imagine a little mechanical motor, about yay big, and that motor is electrically controlled and has a little arm that moves like this. So a little motor, 2 electric contacts causes it to move. As that moves, it's connected to the control cable and it forces it to move up and down. As it spins, it can allow its movement. So if you turn an autopilot on, that shaft behind there has a pin input to an autopilot servo. And when you turn the autopilot on, your input changes into a servo making that input for the autopilot. So it's just a matter of whether I do it or a mechanical servo.
That's something you program it to take you to any particular airport.
Sure, you can use that through different forms of navigation, whether you're using Siri agrees. You can use that whether you're going to, I don't know why Siri didn't say that. I didn't say Siri. Now that I said that, I'm in bad trouble. I guess she's listening to this class. Maybe she's learning something. So you can couple an autopilot to different sources, whether that be radio navigation or GPS navigation as well. And that'll track lateral courses. So it'll say, oh, my course is over here. I'm here. I need to turn left. So I need to add a roll input in this direction. So I'm going to cause the airplane to roll a little bit in this direction. Some autopilots only have roll control or pitch control or yaw control. Most small airplanes were flying controlled two things. It's a two-axis autopilot, usually altitude and heading hold. So an altitude hold allows for pitch up and down. So that's adjusting elevator input, either by physically adjusting the elevator or trim setup, depending on the autopilot design. And then roll to control heading is aileron movement, that it just allows the ailerons to. Now, if you get into fancy airplanes, you can get rudder trim that's connected to an autopilot. I can't think of a smaller plane that has that. You certainly don't need to stress about it. And then as you move up, you can get more and more skilled autopilots. Helicopters even have some autopilots on them. And there's a lot of, even some smaller planes as hangar, the autopilots are pretty complex. They have a lot of cool functions and features and designs. There's a million different products out here. Whether you're using a Bendix King autopilot, these Garmin GFC 500 autopilots are really sweet. You can do a ton of cool things like select a heading or fly an approach or navigate to somewhere, a particular heading, or vertical modes. Like I can descend up and down at certain rates or maintain an airspeed or descend on a preset path. I can maintain an altitude. A lot of cool functions these autopilots can do. And they all work by adjusting the control surfaces through some form of servo. Now, more fancy airplanes aren't adjusting those servos as much as they are adjusting computer inputs to hydraulic systems. That makes sense? Autopilot's not necessary, but we do like it. To keep us on time, do you guys still want to break for a quick second? Or do you want to keep moving? You guys are good to keep moving? If you guys need a break, go for it. Not a big deal. I mean, if you guys want to run out, that's fine. Any questions from anyone online? I assume we're good. Cool.
So with the Warrior aileron, is that a differential aileron?
Yeah, this one is.
Okay.
You we go down the hangar after, I'll show you. It actually moves up more than one than the other. You can you'll notice it when you move it down, go, that moves a lot, and then it comes up, and like, it doesn't nearly move as much up as it does down. Okay, that's the end of the flight controls. Primary, secondary flight controls. Our primary flight controls, can anyone remember the acronym or the three primary flight controls? Here, elevator, aileron, and rudder. Anyone want to name at least 2 or 3 secondary flight controls? Flaps, trim,
Spoiler.
and spoilers. And then another one we discussed was leading edge devices. Good. All right, the electrical system. Everyone's favorite. Everyone loves the electrical system. First, before I talk any more of systems, remember, the airplane you're actually flying in the air, you want it to be intimately familiar with how each of their aircraft systems work. One airplane may work differently than the other. They're all going to have the core same ideas, but one is different than the other. As I mentioned, you probably noticed Piper has a different design than Cessna. And Piper and Cessna think differently than Cirrus. And they think differently in Beechcraft, even though Beechcraft is owned by the same company as Cessna is. But they were different companies years ago. And they all have different designs. So be familiar with your aircraft. Look in your aircraft's owner manual or pilot operating handbook for the exact system. We are going to be talking in general terms about the electrical system, not in detail. Most smaller aircraft are equipped with a direct current or DC electrical system and have some big components, usually a battery, that is a DC battery. Some have 2, most have 1. This will supply electrical power to most of our systems. Now, we also have an alternating current or AC setup, usually driven by an alternator. If you fly an older airplane, you have a generator input, but not really most relevant to us anymore. We're flying most alternator-driven airplanes. This provides AC power. And that AC power from the alternators is usually what charges our battery, because if the battery depleted all the time, we'd have to put a new battery in every flight or recharge it. Your car, same exact setup. You use the battery to start the engine. Once the engine's running, the alternator charges the battery and provides power to the system. Airplane is the same. Cool. But again, most are 14 or 28 volts. A little older. When I say older, I mean 70 on, 14, mid-90s, 2000s on, we're seeing 28 volt systems. Reason was that the 14 volt systems from years ago weren't exactly providing power to a ton of things. Nowadays, we have a ton of glass instruments that are using a lot more electricity. So they bumped it up to 28 volt systems, different designs. I mean, back then, pretty much the only electrical instruments were maybe a radio and a navigation capability. Now we got a ton of different electrical things on an airplane.
Is that why it's not 12 and 24 volts? Because of the, what it's running?
Correct.
Okay.
Yep. And they need to find new ways to charge with radiation things.
Yeah.
Couldn't possibly want to retrofit something from anywhere else. Okay, these slides have a lot of content on them. I'm going to try to talk as much as I can through them. It's good for interaction if you guys want to ask questions or talk about your experiences with cars because they are the same. So a battery. Anyone familiar with electric systems or electricity in general? Anyone work on cars? Anyone want to give me a general description of what a battery is? Sure, try it. What is a battery? Power source, right? It's a power source, right? Anyone familiar with electricity in general that can describe in like a sentence or two what electricity is? And this is a suffrage one. This is something that's harder for us to understand because we can't see electricity all the time, kind of like hydraulics, it's hard to understand, but we interact with it so much. Electricity.
Flow of electrons.
Flow of electrons, right? We usually have a charge, positive or negative, meaning direction of flow. So if I talk about DC current, I'm talking about direct current flowing in a single direction. If I'm talking about alternating current, I mean swapping directions here. This is a flow of an electron from one valence shell, outer shell of an electron, moving from one to the other. That's what we're talking about. If I store up a charge in one location, we're going to call that, as far as we're concerned, a battery. Now, for producing this, we need a producing source. The battery is a maintaining source. So a battery is where we're going to get power from in the event an alternator fails or an alternator is unavailable. So for the wise among us, once the engine is running, provided the alternator works the rest of the flight, true or false, the battery is basically a paperweight. True, once we get the engine running, we don't need the battery anymore. The battery was basically there just to start the engine. Now, in airplanes, we can't just drive off to the side of the road, so the battery stays with us and has a huge function. In the event the alternator fails at some point to providing that charge in AC, the battery can take over that load to get you on the ground. Unfortunately, the battery usually didn't have a ton of time, 10, 15 minutes before it's completely depleted, because it's only a power source as a whole. It's not producing power, it's just storing it and giving it to you at a time. Again, most are 14 or 28 volt batteries. Most airplanes, and we're going to talk about, have an alternator that produces power. That produces AC power. Most of our avionics run AC. There are some things that run a DC power source. There will be a way to swap that power from DC to AC through, anyone know what the term is where you move DC to AC? An inverter, where if you rectify the power from AC to DC. Those are just terms that we use. If you go look at your aircraft systems manual, you'll see different terms like inverters or rectifiers. Those are referring to transferring power from AC to DC or DC to AC. Don't be stressed about it, it's not too important for you. Just know that not everything runs on AC or DC. There are points where they transfer to. So most systems have many components. An alternator generator, we'll worry about the alternator. A battery, switches to run these various components. Bus bar and fuse, don't stress. A voltage regulator, we'll talk about exactly why we need that. And monitoring systems like an ammeter or load meter, and then a ton of wiring to run from place to place. Now, I put this comment in here. Some aircraft have a GPU for external connection. This is usually large aircraft, airliners or these corporate jets out there, to avoid running their own engine and auxiliary power unit or running an engine that burns gas. It's expensive. They take an external power source. That's called a GPU. Most small airplanes, we don't use that. We use the battery to start it, and we rely on the engine for the remainder of that. But if for some reason the battery is not working, All these airplanes have a little plug to put an external power source in there to either charge the battery or to start the airplane and charge the battery. Just know that there are plugs out there. You'll find that in every airplane in the hangar. There's usually an external source. Okay, a voltage regulator. It does exactly what the title says. Now, exactly how it works, I'm not going to get into detail. We don't need to get into engineering too much. The alternator of an engine. Anyone know how an alternator works, or want to describe how electrical current is developed or harvested, if you will? So, okay.
Magnets and
Yeah. Yeah, I'll give you a quick understanding of it. If you have magnets that are near wires, anyone know that, like, anyone think about this? If you send electricity through a wire, it sets a magnetic field around it. Magnets have a field around that. If you have these magnets that touch, their fields break, the electrons move. See what I'm saying here? As we move magnets through a wire's field, it allows for electricity to be built. That's the charge moving, the electrons moving between them. So all you need to do is spin a series of magnets or wires around each other, and they start to produce a charge between them, what we call electricity. That's the basic understanding of an alternator. Now, as you spin that faster, you have a higher output. If you spin it lower, you have a lower output. An airplane spins at many different power settings, full power idle, meaning 27 RPM or 1,000. To regulate that output, we have a voltage regulator. This is what allows that voltage to remain the same throughout it. Mainly, that's the easiest way to understand it. If the voltage regulator stopped working, it would start providing erroneous voltages to different systems that don't use that. So if your particular item, say, uses 14 volts and you provide it 6, it won't work. You'll see the buttons on the screen will stop working and the screen will go away. If you provide a really high voltage, you'll start seeing erroneous movements, erroneous things that shouldn't be right. It's rated to a certain power setting. And the voltage regulator is what regulates the whole system to ensure it's working correctly. Cool?
You might even see smoke.
You might. You know what they say about electricity? If you see the smoke, the magic let out of it.
Yeah.
Have you ever played like a little electric kits, those resistors? If you let one explode, the smoke comes out of it. That's the magic coming out of electricity. Okay, switch wise, we have a master switch. That thing on the right there. Master switch. When turned on, this is providing electrical power to everything that's powered by that only. So in this case, we're going to talk about a master switch, which in most airplanes, we're referring to the battery. One battery, usually, that powers certain things, meaning some of these immediate things here can be powered. These are essentially, like if you lose your alternator, what's powered, which usually is everything, but remember, your battery has a limited time component. Stuff like the lighting on the outside of the aircraft, interior lighting, radios, and a handful of equipment in there. That's what's powered by the battery. Not all airplanes have these powered. For example, the stall warning system in the Cessna 172 is automatic. You don't need a power input. It's all pressure difference. Whereas in a Piper product, there's a little switch that moves that causes that system to work. Again, in the hangar, let me know. But no, this is a general understanding of what that battery switch is controlling. Some will combine that master switch into two halves, the left side being an ALT, the alternator. So if you want to turn on and off the alternator, its output for one reason or another, you can do that on the other side. This is what you would see in a Cessna 172, for example. If you turn it off, it doesn't stop the item from working. It just electrically disconnects it from the remaining portions of the system. That makes sense. Before I continue, I kind of do a little show and tell. Anyone know what this piece here is? Yeah, this is an alternator. If you actually look in here, you can see. I will warn you, it's a little greasy, so do be cautious if you want to come take a look at it. You can actually see the little electrical windings in there that's spinning. This piece is connected to the shaft. I don't know if you guys probably can't see that from here, but inside, as this spin, this is connected to the engine as it spins. This is what spins its output, and we can have different contacts that run out here. This is the actual alternator that's attached into the engine. If you want to come look at it, it's there. It's greased up because it spins a lot, so to avoid any friction. Has a lot of grease. Anyone have any questions on an alternator? Or how to control with this switch on and off? Pretty self-explanatory. A bus bar. All right, anyone want to try the term bus bar, what it could mean?
Series connect.
Yeah, we're a series of connections. So if I have a battery, I can't connect everything to that battery. I run out of space on the battery, right? I get overwhelmed as well. I need protection to it. So imagine if I took a battery and connected it to a metal connection. Sometimes it's physically a piece of metal that can conduct electricity or a wire, or a series of connections and terminals for connection. I can connect the power input, and everything that attaches to it goes to that. We call it an electrical bus bar. It's not a bus. There's an electrical bus, yes. There's no physical bus, just a piece of metal. That's what we call it. It's a bus to power. So it can allow one source of power to be powered to multiple things. So we have different power buses. Commonly, we have a primary bus or an avionics bus, meaning power is connected to the avionics through one bus, power is connected to other things through another bus. For example, a primary bus may have things like a wing flat, if you have an electrical wing flat, landing lights, strobe lights, a flashing beacon, or fuel quantity indicators. Those are what we would be on a normal primary bus. Whereas an avionics bus may have things like autopilot, navigation radios, communication radio, those kind of things. They would be connected to an avionics bus bar. Questions of bus bar, they're a way of delivering voltage from one space to another.
You go back slide.
Sure.
After you take off and you start it.
Yep.
Do you turn the battery off or just leave it on?
No, you'll leave it on. In the event you lose the alternator, you still want the battery to power the system. There will be an indication for that in the cockpit. We'll talk about that in a minute, called a load meter or ammeter. You'll see that source changed. Plus, I should mention, battery charging is connected to the alternator as well. Did I mention that earlier? I didn't. Sometimes I can forget. If you notice, between the actual item in this diagram and the bus bar, there's this little picture. That's usually a fuse or circuit breaker. Can anyone describe a fuse or circuit breaker?
If too many amps are drawn for that circuit, it ends up triggering, flipping, or burning out.
Sure.
Fuse.
Old style fuse design is in a little tube. They don't have a fuse in their car. They had to replace a little tube in there. Basic thought of this is you have a wire inside of a tube you're applying current through, and the wire is rated to a certain current value, amps. If that value exceeds, its current going across it goes up way too high. Usually the resistance bumps up a good bit in there. That heats that wire up, and when it hits a certain voltage or current value, it melts itself and disconnects the connection and shuts that component off.
Prevents the magic smoke.
Exactly, it prevents things from lighting on fire and smoke. Fuses, unfortunately, that when that wire burns, that fuse needs to be physically removed and replaced. It's done. Circuit breakers or thermal circuit breakers do the same thing, except they disconnect and you can reconnect them by moving a switch. Your house has a set of circuit breakers on it. You can move them back and forth. They turn off or on a component by disconnecting it from the system. They also protect it in the same fashion that if a current value is reached, it disconnects. So to protect all of our systems from the possibility that a voltage regulator has gone bad or there's some weird gremlin in the system that causes an issue, there is either a circuit breaker to protect each item or a fuse. Today's airplanes are almost consistently all circuit breakers. You'll see a circuit breaker panel in the cockpit that kind of gives you an indication if one pops, there's an issue in that system. It's all for protecting it. All right, now someone mentioned about the alternator failing in flight lanes, battery on. Yes. How can we tell if the battery is working or not? We have an ammeter or an amp meter that measures current in the system. So how much current we're currently running at. Anyone ever remember, what's the term? Ohm's law from electricity, the electricity current. Voltage is proportional to current times resistance, meaning voltage, I don't want to describe this. Voltage is the attraction or charge difference between point to point, if you will, the total movement. Current is that attraction moving, right? Resistance is our resistance to that movement. Loosely there. Most people don't understand electrical systems well, that's fine. How much current we have is describing pretty much how quickly that charge is moving from one spot to the other. And resistance is describing how easily it's moving.
You relate it to a hose.
Yeah,
So the-
sure, go for it.
The amount of water or the size of the hose is the volts. How fast that water goes through would be the amps.
Right,
And then the restriction would be when.
Squeeze it.
Squeeze it.
yeah.
Resistance.
Yeah, the water meth, like one of the more common ones, I should have brought that one up. I had that in my list of, I had that in my slide notes too. Anyway, ammeter is gonna measure the current in the system. It's gonna measure in amps. You'll see that in the cockpit with a little gauge. That looks like that. Difference. Ammeter versus load meter. Ammeter shows current draw, either charge or discharge. So let me give you an example on the ammeter. Think about the ammeter directly. If you see a charge or discharge, this means the system is either charging the battery or the battery is discharging. In our world, we have two usual primary sources of power, an alternator and a battery. If the system is discharging, to us, that means the battery is providing the power. If the system is charging back up, the alternator is providing the power back to the battery. If you see 0 on it, like this picture, the system is in equilibrium, meaning the alternator is charged the battery, and the battery is fully charged, and the alternator is providing power to the system. As soon as the alternator fails, there's a huge discharge, and now that turns to the battery for its in use. That's what an ammeter is showing. A load meter does not show us whether or not the power is necessarily coming from an alternator or a battery. That just shows us how many amps are being drawn as a total. So if you have an airplane with a load meter, you'll see, say it's at 30 amps in this example, and I extend the flaps. Well, the flaps extend, you'll see it comes up to maybe 45 amps, whatever the current draw on a flat motor is. I couldn't tell you something about. You can see that as you add things to the system, it changes. So again, ammeter shows us discharge charging rate.
What's the normal amp range while a plane's flying?
On a load meter.
Oh, on the ammeter.
On an ammeter, it should show 0. Should. Because the alternator is providing power to the system and the battery is fully charged. If you were looking at load meter as total draw on the system, that's about 25 amps, 30 amps. Depends on your airplane. Some airplanes will have a higher load pull because they have avionics installed in them. Like these older G1000s take a lot of current to draw, whereas your newer G1000s or smaller avionics won't pull as much.
So how would you know if your battery's going dead, such as in a car, you have a voltmeter? And so you can actually see that
Right.
it's not accepting a charge from the alternator, your voltmeter would drop down in its range. Is there anything like that?
Yeah, so in airplanes that are equipped with a load meter, they're usually simultaneously equipped with an ammeter or a digital display. Most cockpits, if the alternator output falls down to 0, it'll give you an indication in the cockpit. Usually a little ALT light will come on or something that indicates alternator failure. That'll be your sign the alternator stopped working. The aircraft's equipped with a ammeter, you'll see it there as well. Load meter is really not necessarily designed to show you whether the alternator is working, to show total system power. So you'll have other indications of that through other sources.
And then how would you know how many volts your battery is producing?
That is a good question. We can't see that from the cockpit on most airplanes. Now, if you're flying an airplane with a newer avionics setup, say a G1000, these glass cockpits, you'll actually see a battery voltage indication. Other airplanes will not give that to you, as it's not the most critical thing for us to know. However, if you wanted to know, maintenance usually checks that on a test bench. They'll pull it out of the airplane and verify that. But usually in the cockpit, there's no way for us to tell that. If the battery turns on and everything's working appropriately during a pre-flight inspection, we know it's providing the power it needs to. However, in a new airplane, you will see actual battery voltage displayed in the cockpit. New airplanes do it, old airplanes don't. They were just lazy. One more part to add. Again, more weight, more price. Okay, I want to ask one theory question and we'll jump into hydraulics and wrap it up for the day. Hydraulics take like 10-15 minutes. Okay, think about an ammeter. At what point do you think, well, let me give you a scenario. We're sitting on the ground, airplane shut off. We walk up to it, we turn the battery on, right? The master switch, battery alternator, we turn that on. What gets powered? Almost everything. Lights,
The bus.
most of our primary buses. Usually an avionics bus won't get power from the master battery. You'll usually need to have a separate avionics switch for that one. In the Cessna 172, I don't see a picture here. There's a separate bus, separate switch for avionics. Many airplanes do. That switch powers the avionics bus bar. In a Cessna, oh God, I can't tell you exactly off the top of my head, but there's multiple avionics buses for different purposes. There's multiple main buses for different purposes. But when we turn the battery on, it usually powers most of our essential equipment. So we got that turned on. We go to start the engine and we turn the engine, we go to crank the engine to start it up. That starter pulls a ton of current initially to get that engine started. So when you start, you'll see a huge load on the ammeter during engine start and on a load meter. The ammeter will show you a large discharge because the battery is what's providing that cranking power to the starter. So you're drawing current out of the battery for a little bit, for 3-4 seconds as you go to start the engine. Once the engine started, you'll see this ammeter sitting over here showing a discharge, meaning we just discharged the battery. The battery is not at its 100% capacity. So the alternator now says, not only do I have to provide power to the whole system, I also have to charge the battery back up. So right after engine start, the next 10, 15, 30 seconds, depending on how quality your alternator is, or how poor your battery is charged, you'll see a slight discharge on that system as the battery charges back up. Or on a load meter, a higher load momentarily while charging the battery up. Once it reaches 100%, it stops charging the battery and it returns to powering the whole system. And then the battery becomes useless in the event the alternator fails, then you need it. But so right after engine start, you'll usually see a discharge. Some people say, oh, I just started the engine, it's discharged. There's something wrong with the battery. Give it 10 seconds. Give it 10 seconds, you got to charge the battery back up. Your car does the same thing. It's just they give us indication of it, so we get stressed about it.
You say discharge, that sounds like it's going to the negative side, it should be going to the
Oh.
positive side.
Yes. It's a confusing term. There's a few confusing terms we talk about in aviation. If anyone's ever looked into the term density altitude, there's another confusing one. I'll describe that one later. Like low density altitude means high density air. High density altitude means low density air. There's just a couple terms we use that don't make entire sense to the world. It just is what we adopted in aviation. Why exactly?
Oh, it makes sense, I mean, you discharge, but it's gonna be on the positive side, because it's throwing more.
Right.
throwing more in.
We want to say discharge being negative in our head, right?
Right.
But when you think about the math, it makes sense. It just doesn't work initially in our head. Okay, hydraulic systems. This one's pretty quick. We don't have a ton of hydraulic system that we talk about. Does anyone here work with hydraulics or understand hydraulic system? Anyone? You would describe hydraulics in a very 1 minute explanation for us? Yeah.
Equal and opposite fluid, hose or piston. You put pressure on it, push it one way, and bring it back in.
Sure. Yeah,
It's
you're
not.
Water hydraulic.
Sure, water can be.
Water.
Not the most efficient source, but it can do it, right? Hydraulic systems on airplanes usually power our brakes. Those are one of the only usual sources we're powering. They can go to other surfaces. You go into larger airplanes and you'll find they control a lot of things. In small airplanes, usually the brakes. If you touch up to maybe a Piper Arrow that has a retractable landing gear, many of those are controlled hydraulically. Some are controlled electrically, some are mechanical, some are different setups. And older airplanes use this stuff for constant speed propellers. Remember I said there was a fixed pitch and a variable pitch propeller? You can adjust that pitch. That's another term for that is a constant speed propeller. We'll talk about that a little further down the road when we talk about propellers here in systems, but just know that. And like I said, larger airplanes, flight controls become hydraulically used as well. Okay, general components of the hydraulic system. There's got to be a pump somewhere to move the fluid around. There has to be some type of filter to keep this fluid in good shape and no contamination. There's usually some form of valve or control, and then usually an actuator. I forgot to put it in here somewhere. There's got to be a reservoir somewhere in here to maintain all that fluid. Most of these aircraft, I didn't mention it, but the battery usually located in the engine compartment or on the tail. The hydraulic reservoir is usually located in the engine compartment as well. Okay, so I'm not going to dive into too deep details. We don't need to understand it's 100% level. Essentially, imagine everyone have a kind of loose concept of a piston inside of a cylinder. Loosely, imagine this this piston here, this tube, if you will, or cylinder, has a fluid on either side. We call it hydraulic fluid, and it's connected to the reservoir, and fluid flows on one side and the other. And there's a pump connected. If I were to pump fluid into here, it would push the piston down. If I were to pump fluid on the other side, it would cause the piston to go up. So all I'm doing is pumping fluid into one side versus the other under a lot of pressure that this pump causes. And that pushes the piston up and down. That causes this rod to move in and out. You connect that to a flight control surface. You connect that to a brake pad that push onto something. Connect it to a ton of cool things to make things happen. But all it is you're applying fluid on one side, usually to move the other. Does that make sense? You're applying a force from one side to the other to get it to move. We use these for brakes usually, so not the biggest thing. There's usually a selector valve. What I mean by that is an ability here to move from one direction to the other. Sometimes you have a single pump that goes in a certain direction. Some will have a reversible pump that move things in both directions. That's not brakes. Brakes go in and then release. A landing gear for extension and retraction is usually one of those reversible pumps. And what I mean by that is a brake will just put fluid on one side and then allow it to release. Whereas a reversible pump will force fluid onto one side, release, and then force fluid onto another side and release. This is what a landing gear in a Piper Arrow has. There's a retraction side and an extension side that allow the wheels to come up and down. So pumps can change. A relief valve is usually installed here. Those are for pressure. Remember, all this fluid is under pressure. Fairly incompressible fluid. That's what allows us to move it around. And because of that pressure, you don't want it to overpressurize or heat up too much. So there's usually some form of relief valve to even out the pressure. Again, we use this for brakes. Anyone have a guess what the fluid color is? There's a few different colors out there of fluid for hydraulics. Red, that's what we'll see on our small airplanes. You move to larger airplanes, you'll see purple, depending on what airplane you use. They're under a lot of pressure. I could not tell you what our smaller airplanes are under pressure, but
So why
a couple
wouldn't
hundred
they,
PSI.
why wouldn't they, why wouldn't they use just regular brake fluid?
Why? It's an airplane. We got to find a new way to do it properly. When you see a high hydraulic pressure system, something like 3,000 PSI, you're looking at a larger jet that's overcoming a lot of aerodynamic force to move landing gear in and out. Brake is not much pressure. You don't need a lot of force to do that. Whereas if you're causing a landing gear to come in or out, you're overcoming all that aerodynamic force with the wind, especially if you're handling a heavy landing gear like a larger aircraft is. So that's what makes that pressure difference. Hydraulic systems, good introduction to them. Did anyone do the reading on hydraulic systems and electrical systems and found them to be a little harder to grasp? Did today help that a little bit? Kind of start to understand it? Good. Again, read your aircraft's pilot's operating handbook for the exact specifics of how your hydraulic flight control or electrical system works. We were talking about things in vague terms. Keep that in mind. Okay, ready for it now. I'll check anyone online can answer to. What is the difference between an elevator and a stabilator? A, B, C, or D? I know, a lot of words. Anyone got an answer?
D.
Bingo. Stabilator is the one with, equipped with the anti-servo tab. The stabilator is the one that the entire piece of the horizontal stabilizer removed and called a stabilator. Whereas the elevator has that trim piece on the back that's visible. So the following is not a primary flight control. Bingo. Elevator, aileron, and rudder are primary flight controls. An aircraft alternator produces DC power. Exactly, that's what the alternator does. That's what our point of the alternator is. What is adverse yaw the effect of? Here we go. All right. Okay, who has not, of those of you who are online, I already have your attendance done. For those of you who are in class, did anyone not sign the sheet? Who has it? Would you mind making sure you get that signed before you leave? Again, I do apologize about our IT issue. Unfortunately, it had its time limit set up on the initial setup, so I had to swap that out to a different version so it would actually run the whole thing. We had the wrong login, that's all. So I do apologize about that. I do appreciate those who showed up and came here. Again, the recording will be up soon. If anyone has any technical issues, email me. You probably won't see me much for the rest of the class. I'll try my best to show up as much as I can. But again, the recordings will be available online. Does anyone have any technical issues with getting their transcript email? Any issues with that? Again, if you miss a class, just notify me or an instructor so we can get your grade set up. If you do get a transcript and you see a discrepancy on there, just let me know. It's not an issue. I can go fix it. Other than that, read the book, study, and email me with questions. I'll send information out as we go through the course. But again, stay curious. That's all I can say. All right. And again, if you guys want to stay a few minutes, I'll be down the hangar to show you some of these control surfaces on an airplane. All right. That's it for everyone online. Take care now.